What's up, everybody? It's Dan from Sage Math Tutoring and covering a couple calculus problems I was working on with a student today, and there were a couple problems that were pretty challenging, and I wanted to cover them. And this one in particular, this was kind of the first one that we came across, and I'm of course now kicking myself when it comes to this. This one, out of all the problems in this whole video, this is the one where I actually paused and sort of did some research and gave myself some help with. Every now and then you have to do that. Uh, I think the the principle that I want to share with my student watching, though, is the following. Imagine you had, I don't know, something like like this, right? Um, And, maybe you wanted to take the integral of that. Well, that's kind of challenging, right? I mean, if you try u substitution, you could treat the bottom like it's u, um, and then you would find that nothing's really going to cancel this x out. You could try calling x u, and then you'd still not be able to really do much with it, unfortunately. But there's all these like weird ways of like roughing up the integral to make it so that you can perform the integral. There are ways beyond even using u substitution or integration by parts. And one way is to literally bust out long division. So that's the insight that I needed earlier, is the fact that you could actually do long division on this. Now, what would that look like? That would look like x is divided by, let's just make it x plus 1, right? Now it's x plus 0. Hopefully my student watching agrees, right? And then you just ask yourself, okay, this times what would give me the x? Or we could say this x times what would give me that? Well, obviously that's 1, right? And then you do the thing where it's long division. So that it's like x plus 1. And then you would do a little subtraction, a little subtraction. These cancel. And then you have a -1. Now that is the remainder. Now, hopefully my student watching remembers what to do with the remainder um, when you're sort of writing the final answer. The final answer of this division problem is the quotient, which is the green one, right? Plus the remainder over the divisor. So that turns out to be plus -1 over the divisor. So this could be rewritten as that. Now, that is something that we could totally take the integral of, because we all know what that would become. And now there's no variable up here, and this is a degree of 1. So I think my student watching recognizes that x plus 1 would become the u, and this would be sort of an ln situation. Okay. So I really think that that was the missing principle that we needed before. Um, so you could, of course, call x u and see if that would do anything. But I think you'll see that there really isn't a pattern for that. I mean, you look here, this has a square root, like, the derivative of inverse sine, that's got a square root over the entire 1 minus x squared. That's not really happening here, right? This scenario is not happening, and this is not happening either. So even when you kind of look at the most common sort of derivative patterns, it looks like maybe this is trying to happen, but it's not quite, right? So I'm going to say you kind of take those sort of famous patterns off the table. And we also have these over here, which, we could look at. And this has a radical over the whole thing. That's clearly not happening. This doesn't even have any radicals. So it's just not looking good when it comes to using those, right? So I think my point is with that is that I don't know if I want to call x u, okay? But maybe we could call radical x u, right? And we could say u is equal to radical x. Now, of course, that's code for x to the 1/2. The derivative of that is, 1 half x to the negative 1 half. And really, at the end of the day, that's 1 over 2 radical x dx. And there should be a dx here. I think my student also would recognize that dx is therefore equal to 2 radical x du. Now, I think another thing that's really noteworthy here, and in my opinion, this is one of the things that makes it tricky, is to acknowledge that, anytime, since u is equal to radical x, anytime you see a radical x, you could replace it with u. So this could be rewritten immediately, which is a beautiful thing, as 2u du. Now, why do I care about that? I care about that because when you sort of substitute u back into this thing, you don't want any traces of any x's anywhere, right? You want it all to be in terms of u. So, we're kind of moving in that direction, right? So we therefore have 3 over 1 minus u. And instead of writing dx, I'm going to write this thing off to the side. Okay, so hopefully that's very clear. I'm going to move this up to give myself room. All right. So great. The blue 3 and the yellow 2 turn into a 6, and that could go on the outside. And then lo and behold, we have u over 1 minus u. Now, for my student watching, I think you probably know what's coming. It will be the long division. Okay, so we were looking at the pattern earlier today, and the pattern turns out to be nothing more than long division. So let's take a look. If you were to do long division, it would be u divided by, and I'll just say negative u plus 1. So this is u plus 0, right? So you could say, okay, negative u times what would give me a positive u? Well, that would be a negative 1. So then, this binomial times negative 1 would be u minus 1. But then we need to remember to quote unquote subtract this, which changes the sign. So this would become a 1. Now that's the remainder. So we have the quotient and we have the remainder. So how would you write the final answer of this long division? Well, you have a blue quotient, you have a green remainder, and you have a yellow divisor, right? The answer would be the blue quotient plus the green remainder over the yellow divisor, which is just that, right? So therefore, we could rewrite this as that, okay? So notice there's no partial fractions, anything. There's no integration by parts either. We at least did not do that today. Perhaps on the rest of the review sheet, you have to do some of that. But anyway, this could obviously be split, right? So we have a well, I'll just say 6 negative 1 du plus 6 1 over 1 minus u du. And let's just do it one at a time. This, first of all, becomes negative 6 du. Now let's just process that. That would be negative 6 u plus c. But we'll worry about the plus c later. Let's worry about substituting radical x back in for u afterwards. Over here, that would be an ln situation, okay? That would be, oh man, it's like u substitution within u substitution. Oh, God. Let's call A 1 minus U. dA would be negative du. Du, therefore, is equal to negative dA. So that might be crazy, but we have 6, 1 over A, and instead of writing du, we're going to write negative dA. And that would therefore be negative 6 over, 1 over A, integral of 1 over A dA. And hopefully my student watching acknowledges that that's going to be an ln, right? So this one's a little crazy, right? That's going to be, I'll keep it in red, ln A plus C. Now what was A? A was 1 minus U, right? So therefore, I'll just keep it all in black now, ln of 1 minus U plus C. Okay, so what was U? Again, U was radical x up here. Okay, so great. Negative 6 radical x minus 6 ln 1 minus radical x plus C. I'm really hoping that's the answer. I'm going to check right now. So according to the answer sheet, this is the answer. Now let me rearrange my answer to, you know, compare apples to apples. Yeah, so we have a problem here. Obviously we're good here. Obviously we're good with the C. This right here, I'm wondering if somehow this actually equals that. So I paused the video and I tried a few things. I even tried setting these equal to each other, and I did not get infinite solutions. I did get a solution of x equals 0. If you set this equal to that, I got a solution of x equals 0. Now what that means is that these are not, there's only one value of x that would make these equivalent. So therefore, this does not equal this thing for all values of x. So what I did is I, got a second opinion from ChatGPT, and ChatGPT agrees with this answer. Okay. And disagrees with that one. So I'm going to bring in what ChatGPT says right now. Let's see. Okay. So ChatGPT, upon me asking, says it thinks the answer sheet has a typo. The original problem, 3 over 1 minus radical x. First of all, let's just confirm that. 3 over 1 minus radical x, yeah. The correct answer is that. So that's what we said. I'll blow that up a bit. That's what we said. What I said. Yeah, negative 6 ln that minus 6, right? So ChatGPT agrees with my work. And then what else did I say? So for my student watching, I think this is like super annoying. you know, um, I mean, I don't know. ChatGPT agrees, but the chances that there be a typo on the review sheet, answer key, I don't know. It's kind of tough, but I feel like, the fact that ChatGPT agrees with my answer means that the case could certainly be made for what I did, right? The answer sheet says this, right? That would match a different problem. That would match this. Hmm. Yeah, yeah, exactly. Yeah, and these are not the same, right? So here's the original problem. This is the actual problem. And the answer for the answer sheet, according to ChatGPT, is the answer to this guy. Now, these do not equal each other. Am I wrong? Like, to turn that 3 into a negative 3, yeah, you'd have to factor out a negative 1. But that by factoring out a negative 1, that would make this one negative, right? It's not negative over there. So the answer sheet likely accidentally used 1 plus radical x instead of 1 minus radical x. Yeah, so for my student watching, we hit this problem right away. This is like literally the first problem we friggin' did. And part of what made it so frustrating is I couldn't understand how this could be the answer if for no other reason than I really felt like that should be a minus in there. So anyway, for my student watching, I think we're on the right track. I really don't like to be cocky about this kind of thing because I've had plenty of times where I arrogantly said that the answer key is wrong and it turned out to not be wrong and I was wrong. So, I don't want to be like that, but I mean, we do have a second opinion from AI. So, anyway, hopefully that makes sense. Let's move on to the next problem. For my student watching, just rewind this, pause it, go through this. I would say try all of these again, even after watching this video, try all of these again yourself. Okay. Okay. So this one is straightforward. This is one that my student and I were able to get, but I just want to kind of walk through it again. So it is the case that u could most definitely be 3 theta. Du would therefore be 3d theta. And again, this one's very straightforward. You could just divide both sides by 3. Um, so it's like that. And let's see, we've got secant of u, and instead of d theta, I'm going to write du over 3. And of course, a 1/3 can be taken out, right? So let's see. The integral of secant, if you look at the chart, is this here. So for my student watching, you might need to memorize that, not so sure, but I will capture that. Good to just double check and ask yourself if you need or if you're going to have a reference guide. So let's see. Do-do-do-do. Clearly, it's just going to be 1/3 ln secant of u plus tan of u plus c. And since u is 3 theta, we can finally replace that. And we're looking at secant of 3 theta plus tan of 3 theta plus c. So that is problem number 14. Okay, so this is one that at first was a bit challenging, but then it sort of clicked. So let's see. For my student watching, I think one of the things to recognize is that when you have sort of a binomial or a trinomial even on the numerator, in the numerator, there is at least the option of sort of splitting the fraction apart. And what I mean by that is you could always split this into this, right? And for my student watching, that is pretty useful because then you could just do each integral separately. And in fact, I'll even write it that way. So I will write it such that we will be doing this one separately and this one separately, okay? So that turned out to be the winning move earlier today when we were working on it. It is the case that anytime you have these sort of numbers here, you can bring them out front, right? So this one just becomes this. And of course, this other one becomes the following. Yeah. So great. Now, um, you might be looking at this and wondering, okay, what the heck am I supposed to do from here? Uh, there's a couple things that should stand out, I would say, for both of these. First of all, the k squared plus 1 on the bottom for my student watching, I think really that should be reminiscent of something along these lines here, where that's some constant squared plus u squared, right? So it's almost like the u is the variable being squared, and a in this case is the constant. And that would turn into this. Now, I think there's another way of seeing it too. Yeah, another way of seeing it also. This is sort of like a really comprehensive way of seeing it, but I actually want to draw my students' attention to this one, where we have this common derivatives reference guide. We can see that when it's 1 plus a variable squared, if we were to sort of take the integral of that, right, that would just become this. It would become inverse tangent or arctangent, right? So I think that is something to acknowledge. Now, for my student watching, I will actually send you these, okay? Again, this one is a little bit more comprehensive. First of all, it's talking about taking the integral, first of all, right? Um, but it's important that you understand that the a is whatever constant is being squared in this position, and the u is, in a sense, the term that contains the variable, we could say. All right, but this might be a little confusing. You might want to instead focus on just thinking backwards from here. This is very much applicable to this problem. So the reason it's applicable is because this is the exact same structure as that, right? Um, we have a 1 on the top. Here's a 1 on the top. You have a variable squared. Here's the variable squared. You have the 1. You have the 1. So that is definitely a good thing. In fact, we could just process it now, right? So that will literally just be inverse tan or arctan of k, and we'll say plus c. Now, this other one, this other one turned out to be not too bad. This is the one for my student watching where I kind of made it more complicated than it needed to be. Let's go off to the side with it. Let's acknowledge that, of course, uh, you know, you have this on the bottom. Of course, it's making us think of that arctan, but we already sort of exhausted that arctan situation over here. So there must be something else that we can do here. And I think my student watching probably recalls that, yeah, we can treat the bottom part as u. And then derivative of that would be this. And dk would therefore be du over 2k. And then we would have k over u. And instead of writing dk, we're going to write this, right? And of course, that's a beautiful thing because this k will cancel with that k. And then we have this 2 that kind of goes out, and that would be 3 over 2, integral of 1 over u du. And this is sort of a pattern that I would say you want to get really familiar with, where that does become ln u. So that is going to be 3 halves ln. I guess I'll throw that in, what's it called, the absolute value symbols. So u is k squared plus 1. So, of course, we are looking at 3n of k squared plus 1. And then it would be plus c, but we already sort of have the plus c. So I think my student watching recognizes that we could just bring that over, and that should be the answer to that one. Okay, so that is problem number 27. Okay, so I think for this one, obviously there's a relationship between secant and tan. One thing I think worth noting, let's kind of brainstorm the various relationships that like we know to be true. That happens to be true. This happens to be true. The derivative of secant is that. And what else? What else? What else? Hmm. I mean, this is just saying the same thing in reverse. Okay, so I think my student watching would agree that these are related, obviously, right? Um, so when looking at this, one thing that I would like my student watching to recognize is that, to put secant and tangent like next to each other seems to be, I don't know, useful, I guess. So, you know, like this could be rewritten. I think my student watching would agree that this could be rewritten as this secant x tangent x, right? Because it's almost like you could sort of take out a secant tangent out of that and put it off to the side. And then you would have that. So the reason I'm thinking along those lines is because, like, if we were to treat secant as the u, well, the du would be that, right? So there might be something to be gained from making secant the u, because the du would be that, and usually this ends up in the denominator, and that would like cancel that, right? So anyway, let's try it. So we have u equals secant x du, of course, equals secant x tan x dx, and then like I said, that secant x tan x ends up in the denominator. So yeah, great. This therefore could be rewritten as u squared tan squared x. Um, this thing, and instead of dx, we can write this thing. Okay. And the cancellation that I was just talking about can happen now. Great. So we have this. So I looked up the Pythagorean relationship because I needed a reminder of it as it pertains to secant and tan. And that is this one. So these Pythagorean relationships are going to be important. So it is the case that anytime you see a secant squared x, you can replace it with that. But it's also true that anytime you see a tangent squared x, you could replace it with this. And and we also know that secant is u. So since we already have a u, we want this in terms of u, right? Because we don't want any x's here, right? So we want to get everything in terms of u. So let's rewrite tan squared x in terms of u. Tan squared x is really equal to u squared minus 1. So yeah, that should be the ticket then. Okay, for my student watching, I'm sure you would agree. So I have u squared times u squared minus 1 du. Okay, yeah. Just great. This is the home stretch, clearly. Taking the integral of that, we have u to the fifth over 5 minus u cubed over 3 plus c. And what is u? U is secant, right? So, wow, good time. Secant x over 5 minus secant over 3 plus c. Yeah, so that should definitely be it. I'm feeling good about that. I'm going to check the answer and make sure that I am correct. So let me just double check. Looks like that is indeed the answer. So, okay, that's how you do that. Okay, so um, let's see. I feel like the things that might be applicable would include that. Um, I also feel, I don't know, maybe this will be applicable. Not so sure. Hmm, this might be applicable for using U substitution. So anyway, just kind of getting a sense of it. And also we have that Pythagorean relationship to sort of keep our eye on, right? So we have tan squared x equals secant squared x minus 1. Okay. So, hmm, hmm. Well, this here could be useful in that we really have tan squared x squared happening. And I think a route to try is to throw this in there. So this is certainly true. Is that helpful? Hmm. Is that helpful? Might be helpful. I mean, this is going to become a trinomial, right? So, if you were to FOIL that, it would become secant to the fourth minus 2 secant squared plus 1, right? Well, I mean, that could be split, right? That could be split into three different integrals. I mean, in a way, this is just like the way I experience this is like a big block of like, what are you going to do with that? It's almost like a dense block of ice. But what we're doing is we're kind of breaking it apart a little bit. And, you could just do this. This might be something. I mean, the secant squared is going to just be tan. So that's a beautiful thing, right? Um, I mean, I feel like these we're good to go. I mean, this one might be interesting. These you should be good to go though. Okay. So um the integral of secant squared is right here. That's just tan. So you can't get more straightforward than that. So we have minus 2 tan x. This is just going to become x. And then we have the plus c. So hopefully my student watching agrees that this is just x. But then we have this situation. Um, the Pythagorean relationship, once again, is here. And we can remind ourselves that secant x is equal to tan squared x plus 1. Therefore, anytime you see a secant squared x, you could replace it with that. So for my student watching, I think a lot of it just has to do with sort of splitting these up and experimenting with throwing in like the Pythagorean relationship. So for example, this of course could be split up into this, But that could be split up into this, right? With all the rest of it here. Um, how is that useful? Is that useful? Hmm. Well, oh, okay. Yeah. Yeah. Don't distribute this. We could, if you take the derivative of tan, that's secant squared, right? So we could call u tan x. Du is literally secant squared x dx, right? So we have dx du over secant squared x. So yeah, that's going to cancel that, right? So, okay, this is all probably going to work out. So we have secant squared x times this sort of u squared plus 1. Yeah, right? Yeah, I think my student watching sees this is all going to come tumbling down in a good way, like a house of cards right now. Um, cancel, and look at that. That's going to be great. And we have this, of course. And obviously, we're looking at u cubed over 3 plus u. And then it's like this. And what was u? U was tan, right? So that's tan cubed x over 3 plus tan x. And then it would be the rest of this. So I think that's right. I'm going to check the answer. 1 second. Yeah, so this is correct. However, the answer said, what did the answer say? The answer said that it's this, right? Some of you watching may have caught my issue right now. So I'm looking at this blue answer and I'm wondering what the heck. But it turns out these are like terms, right? So you could combine those and it would turn into that. So yes, the answer agrees with me. Okay, so that one's crazy. For my student watching, yeah, quick recap. Maybe brainstorm some of the relationships, remember the Pythagorean relationship, um, acknowledge that this is kind of like you might try a few different things and it ain't working. So maybe you could try breaking it up by just replacing it and kind of seeing what happens. That would turn into this quadratic trinomial, or it's really quartic, but you could kind of think of it as quadratic. So that would turn into that. This could at the very least be split. These two were really easy to deal with, and you had to deal with this. But then we're reminding ourselves once again of the Pythagorean relationship where this secant to the fourth could be split in that manner. And then insert tangent squared x plus 1, use substitution from there. So yeah, for my student watching, I'm sure you agree. That one is a little crazy. Okay, well, whenever I see the E, I become happy because at the very least, taking the integral of E is pretty easy, right? Now, of course, it's more complicated because there's a sign up there. But I think my student watching would agree that the intuition is probably to call that exponent u. And let's do that. So du, of course, would be cosine of x dx, right? Yeah, so this one turns out to be pretty easy as well. I'm sure my student watching would agree. Because things will just sort of cancel, right? So we have cosine of x, e to the u, and instead of writing dx, I'm going to write this instead. And lo and behold, the cosines cancel. And what do you know? We have e to the u du. Now, what is that going to become when you do the integral? Well, it's just itself, right? And then we could replace the u. We know that the u happens to be this sine x up here and plus c. So I think my student watching would agree that one's not too bad.